Good day everyone, my name is Diana Galbena and my topic is about the discrete probability distributions, and this is a continuation report of Marlica Lunod and Summer Conquera. My topic is about the discrete probability distribution. Aside from binomial distribution, there are other types of distribution. What are the other types of distribution? First, the multinomial distribution. Second, the Poisson distribution. Third, the hypergeometric distribution. Fourth, the geometric distribution. We will tackle about multinomial distribution. What is a multinomial distribution? Multinomial distribution is used to find probabilities in experiments where there are more than two outcomes. It is different from binomial distribution because binomial distribution only focus on two outcomes, while derived from the word multi means more than two. Multinomial distribution focuses on more than two outcomes. For example, a survey might require the responses of approve, disapprove, or no opinion. Or a person may have a choice what he will do on Friday night. It is either he will go on a movies, go on a dinner, basketball game, play, or go on a party. It is a probability experiment that satisfies the following four requirements. First, there must be a fixed number of trials. Second, each trial has a specific but not necessarily the same number of outcomes. Third, the trials are independent. Fourth, the probability of a particular outcome remains the same. Formula for the multinomial distribution: if x consists of even e sub 1, e sub 2, e sub 3, ellipses to e sub k, which have corresponding probabilities p sub 1, p sub 2, p sub 3, to p sub k of occurring, and x sub 1 is the number of times e sub 1 will occur. X sub 2 is the number of times e sub 2 will occur. X sub 3 is the number of times e sub 3 will occur. Then the probability that x will occur is probability of x is equal to n factorial over x sub 1 factorial times x sub 2 factorial times x sub 3 factorial ellipses to x sub k factorial multiplied to p sub 1 with the power of x sub 1 multiplied to p sub 2 with the power of x sub 2 ellipses to p sub k with the power of x sub k, where x sub 1 plus x sub 2 plus x sub 3 ellipses to x sub k is equal to 1, and p sub 1 plus p sub 2 plus p sub 3 ellipses to p sub k is equal to 1. For example, in herbicides, it was found that 65% of individuals use herbicides for commercial purposes, 27% of individuals use herbicides for agricultural purposes, and 8% of individuals use herbicides for home and garden purposes. Of 5 people who said they use herbicides, find the probability that 3 use them for commercial purposes, 1 use them for agriculture purposes, and 1 use them for garden purposes, home and garden purposes. It is given that n is equal to 5, x sub 1 is equal to 3, x sub 2 is equal to 1, x sub 3 is equal to 1, p sub 1 is equal to 0.65, p sub 2 is equal to 0.27, and p sub 3 is equal to 0.08. Substituting in the formula gives probability of x is equal to 5 factorial over 3 factorial times 1 factorial times 1 factorial multiplied to 0.65 with a power of 3 times 0.27 with a power of 1 times 0.08 with a power of 1 is approximately equal to 0.119. There is a 0.119 probability that if 5 people are selected, 3 will use herbicides for commercial purposes. Person will use them for agricultural purposes and 1 person will use them for home and garden purposes. Next is the Poisson distribution. It is a discrete probability distribution that is useful when n is large and p is small, and when the independent variables occur over a period of time. It can be used when a density of items is distributed over a given area of volume, such as the number of plants growing per acre or the number of defects in a given length of videotape. A Poisson distribution is a probability experiment that satisfies the following requirements. First, the random variable x is the number of occurrence of an event over some interval like length, area, volume, period of time, or etc. Second, the occurrence occur randomly. Third, the occurrences are independent of one another. And fourth, the average of numbers occurrences over an interval is known. Formula for the Poisson distribution. The probability of x occurrences in an interval of time, volume, area, etc. for a variable where Greek letter lambda is the mean number of occurrences per unit, which is time, volume, area, or etc. The formula is the probability of x occurrence to lambda is equals to e minus lambda times lambda to the x over x factorial, where x is equal to 0, 1, 2, and so on. The letter e is the constant approximately equal to 2.7183. E is a Euler. For example, the typographical errors. If there are 200 typographical errors randomly distributed in a 500-page manuscript, find the probability that a given page contains exactly 3 errors. The lambda is equals to 200 over 500 equals to 2 over 5 or 0.4. 0.4 error per page since x is equals to 3, substituting into the formula yields probability of x occurrence to lambda is equals to e minus lambda times lambda to the x over x factorial is equals to 2.7182 with a power of negative 0.4 times 0.4 with a power of 3 is equals to 3 factorial is approximately equal to 0.0072. Thus, there is less than a 1% chance that any given pages will contain exact 3 errors. Next is the hypergeometric distribution. A hypergeometric distribution is a distribution of a variable that has 2 outcomes when sampling is done without replacement. It is used when there are 2 outcomes and sampling is done without its replacement. The probability experiment that satisfies the following requirements has 3. There are a fixed numbers of trials. Second, there are 2 outcomes and they can be classified as success or failure. 3, the sample is selected without replacement. Formula for hypergeometric distribution given a population that only 2 types of objects, females and males, defective and non-defective, successful and failures, or etc., such that there are items of one kind B, items of another kind, and A plus B equals the total population. The probability of X of selecting without replacement of a sample size N with X items of type A and N minus X items of type B is probability of X is equals to AC of C sub X times B C sub N minus X over A plus B C sub N. The basis of the formula is that there are as A C sub X ways of selecting the first type of items, B C sub N minus X ways of selecting the second types of items, and A plus B C sub N ways of selecting the items from the entire populations. For example, the house insurance. A recent study found that 2 out of every 100 houses in the neighborhood have no insurance. If 5 houses are selected from 10 houses, find the probability that exact one will be uninsured. The solution is, in this example, A is equal to 2, B is equal to 8, X is equal to 1, and N minus X is equal to 4, where the probability of X is equals to 2 C sub 1 multiplied to 8 C sub 4 is equal to 10 C sub 5 is equal to 2 times 70 is equals to 252. We multiply the 2 times 70, which result to 140 over 252 is equals to 5 over 9. It is approximately equal to 0.556. Where there is a 0.556 probability that out of 5 houses, 1 house will be uninsured. Lastly, the geometric distribution. Distribution can be used when an experiment has 2 outcomes and it is repeated until a successful outcome is obtained. An geometric distribution experiment is an probability experiment that satisfies the four requirements. First, each trial has 2 outcomes that can be either successful or failure. Second, the outcomes are independent of each other. Third, the probability of a success in a same for each trial. Fourth, the experiment continues until a success is obtained. The geometric distribution tells us when the success is likely to occur. The formula of geometric distribution, Fp, is the probability of success on each trial of a binomial experiment, and N is the number of the trial at which the first success occurred. Then the probability of getting the first success on the nth trial is P of N is equals to P multiplied to 1 minus P with a power of N minus 1, where N is equal to 1, 2, 3, and so on. For example, a die is rolled repeatedly. Find the probability of getting the first 2 on the third roll. To get a 2 on the third roll, the first 2 rolls will be any other number except a 2. Hence, the probability is P, not 2, not 2. 2 is 5 over 6 multiplied to 5 over 6 times 1 over 6 is equals to 25 over 216. Now, by using the probability, you get the same results. P of N is equals to P multiplied to 1 minus P with a power of N minus 1 is equals to 1 over 6 multiplied to 1 minus 1 over 6 with a power of 2 is equals to 1 over 6 multiplied to 5 over 6 with a power of 2 is equals to 25 over 216. Hence, the probability of getting the first 2 on the third row is 25 over 216. And that's all. Thank you for listening.